Hi there, welcome back. Now that we have this new tool in our toolkit about how to take a double integral when the domain looks like a function that is behaves like a polar region, let's see how to apply that to a situation when we're given a double integral that looks like it might be complicated. Um, here's an example. We want to calculate this double integral. And you see we have an integral from 0 to 3, an integral from negative square root of 9 minus x squared to positive square root of 9 minus x squared, something dy dx. One technique that we have for calculating a double integral is interchanging the bounds. We're going to have this new technique where we convert our integral into a polar integral. The key here that says, the hint that we want to do a polar integral is coming from these bounds, where we see that y equals square root of 9 minus x squared. That's a circle. And when we have circles, circles tell us we probably want to use some polar coordinates. So let's draw a picture and see what's happening. What do we have? We have an integral. We have x goes from 0 up to 3, and then our function goes from, so if we have y is equal to negative square root of 9 minus x squared, that's the same thing as y squared is equal to 9 minus x squared. X squared plus y squared is equal to 9. So that's telling us we're dealing with the bottom half of a circle and the top half of a circle, and that this is our domain D. All right, so you look at this picture, you see a circle centered at the origin, you should think, oh, that's a really nice region if we think of it as a polar rectangle. So as a polar rectangle, this is r is between 0 and 3, and then theta, well, it goes up to pi over 2, and then we have to continue this backward from something to go through 0 and go up to pi over 2, so theta starts at negative pi over 2. So this, if you look at this region is the same as that region, but all of the bounds here, all bounds are constants. And we like integrals where all the bounds are constants. Okay, let's now take our integral and rewrite it. So what I've taken what I had on the previous slide, I'm putting it here. And what we want to do now is we want to integrate. So we want to integrate this where we have r goes from 0 to 3, theta goes from negative pi over 2 to pi over 2. And then we have, what's this function now? So we have to be careful about two things. We have to be careful about translating our x's and y's into r's and thetas, and we have to be careful about changing our dA's into r dr d theta. All right, so x cubed plus x squared xy squared is what? So it's r cosine of theta cubed plus r cosine of theta times r sine of theta squared, all times r dr d theta. Okay, and so let's simplify this. What do we get? We have an r cubed cosine theta, cosine cubed theta, plus r cubed cosine theta sine squared theta, all times r dr d theta. Let's now put the r's together. We have an integral from r equals 0 to 3. Integral theta equals negative pi over 2 to pi over 2. we have an r to the fourth, and then we have a cosine cubed theta plus cosine theta sine squared theta, d theta, dr, and d theta. All right, so I'm looking at this, and what I'm seeing is if we factor out a cosine of theta, we get a cosine squared plus sine squared of theta. So this here is cosine of theta times cosine squared of theta, and this is cosine theta times sine squared of theta. Cosine squared plus sine squared equals 1. So what we get here is we get this integral, r equals 0 to 3, theta is equal to negative pi over 2 to pi over 2 of r to the fourth times cosine of theta, d theta dr. Okay, now because this is a polar rectangle, we have a function of one variable times a function of another variable, we can split that integral into two pieces. So this becomes the integral from r equals 0 to 3 of r to the fourth dr times the integral from negative pi over 2 to pi over 2 of cosine of theta d theta. Right, this is only true, we can only do this because we have a rectangle and because we have one function of r times one function of theta. All right, and then that's going to give us r to the fifth over 5 evaluated from 0 to 3 times sine of theta evaluated from negative pi over 2 to pi over 2. And so in the end, what do we get? We get 2 times 3 to the fifth over 5. And that's our answer. So, uh-oh, there I am. All right, so that's how we can convert an equation that's in terms of a not pleasant region in terms of Cartesian coordinates into a very pleasant example in terms of polar coordinates. All right, I'm going to do another example, but let's do that in another video. See you shortly.